Okay, in this video today we're going to be talking on the mechanism of nucleophilic substitution reaction in alkyl halides. Now, basically, there are two mechanisms that have been proposed for nucleophilic substitution in alkyl halides, and the basis of this mechanism, as you can see from here, is kinetic studies. That is like the studies of the rate, like the study of the rate of the reaction and the way they vary with factors such as change in concentration, temperature, and solvents. For other substances, we can also consider pressure, but as we're dealing with alkyl halides, these are the three major factors that we're going to consider for changes and for the reaction rates. So let's go on. Now, factors that the kinetic substitution reaction rate in alkyl halides depends on. Those are the factors I told you before. I'm just like bringing three of them together, just like, yeah. So now these three factors, they include concentration of each agent, that is the concentration of the alkyl halide and the nucleophile, because these are the two basic factors. These are the two basic like reagents that we're going to be using in this reaction, the substitution reaction. So the concentration of the alkyl halide and nucleophile. We all know what a nucleophile is. If you don't know like what a nucleophile is, let me just give you a very good example, like a Lewis base. Like a nucleophile is always like a proton donor, is always looking for like a particular like place for it to like donate its proton. That's why I gave the example of a Lewis base. Lewis base are electron pair donors. They have excess lone pairs of electrons, so they can actually donate to a bond which lacks, or which is like lagging, or which lacks electrons, so to actually stabilize the bond. So that's what a nucleophile is. Now the second type of alkyl halide. Now there are three different types of alkyl halide depending on the structure. We all know the primary alkyl halide. That is when only one carbon group is attached to the alpha carbon. That's the primary carbon, the alpha carbon. Now the secondary alkyl halide, when two carbon groups are attached to the alpha carbon. Let me just call the carbon groups alkyl groups. When two alkyl groups are attached to the alpha carbon, and tertiary when three alkyl groups are attached to the alpha carbon. Now the polarity of the solvent used. Now depending on solvent used, like polarity of solvents, there are two types of solvents. We have the polar and the non-polar. The polar can still be divided into polar protic and polar aprotic, and in this we're going to be using polar protic and polar aprotic. I'll explain that later on, but now let's just keep going. Nucleophiles include all Lewis bases. Like I said earlier on my definition of nucleophiles, nucleophiles includes all Lewis bases. Now you can see examples of Lewis bases here: OH, CN, RO, RCOO, and so on. Other examples that we can actually include are water, H2O, ammonia, NH3, and so on. Those are other examples of Lewis bases. But for now, let's just like use all these ones. But just know, nucleophiles include all Lewis bases. Now, all of these here, they are Lewis bases. They have lone pairs of electrons. If I want to demonstrate, I can use water to actually demonstrate this. Water is O, H, H. Now we know that the oxygen has 6 electrons. Like 6 electrons in its outermost shell, so 6 electrons. Hydrogen has 1 electron in its outermost shell. Since there are 2 hydrogens, so I have 2 times 1. That's going to give me 8 bonds. And in the line bond, there are 2 line bond is equal to 2 electrons, 2 dots electrons. And let me just put the dots, 2 dots electrons, and yeah, that's just it. So now we can see that there are 2 line dot electrons that have been used up. So we are expecting to have, since there are 8 minus 2 times 2, because the line bond includes 2 electrons, 8 minus 4, and that will give me 4. So there are 4 extra electrons. So we just include the electrons from there. The first one, the second one, the third one, and the fourth one. And now we can see that water has like 4 lone pairs of electrons, and these lone pairs of electrons can be donated, and that's why you can see water forms complexes and so on. Example, ammonia also forms complexes. Example, ammonium ion NH4 is a complex, and that's just the reason, because they are prone to like form complexes. and that's why they are also Lewis bases. Okay. Now, types of nucleophilic substitution reaction in alkyl halides. Now, there are basically two types of nucleophilic substitution in alkyl halides. The first is substitution nucleophilic unimolecular, as we can see the short form, which I'm going to be using most of the time. That's SN1. The second is substitution nucleophilic bimolecular, also called SN2. Now, these are the two basic nucleophilic substitution reactions that I'm actually going to be talking about. There are also other types of these are just the two basic ones I'm actually going to be talking about under substitution reactions. So let's go forward. Now we're starting with the first one, substitution nucleophilic unimolecular. That's just the name. If I want to actually just include it in brackets, SN1, like I said earlier. Now, this reaction follows first order kinetics. What's first order kinetics? There's this. That's just this. This is like the equation for first order kinetics. You know the order of a reaction. That's under rates of reactions. It's just like if you've done rates of reaction, you have to know what I'm talking about when I'm talking about the order of the reaction. So on, that's the power which the concentration is raised to, and that's why I put 1. I just put 1 so just to indicate that that's what I'm actually talking about, which means that the rate equation given to us is rate is equal to K, that is rate constant, and the concentration we can see later on that is alkyl halide, the concentration raised to the power 1. That is, it's following first order kinetics, and this is the rate equation for first order kinetics reaction. Now, in SN2 reaction mechanism, only the concentration of the alkyl halide is considered, so the rate of the equation can be given as this. So this ends up becoming the rate of the equation. Why is this ending up becoming the rate of the equation? Because in SN1 reaction mechanism, we do not consider the nucleophile. The nucleophile doesn't actually take part, or is not essential in determining the direction or the rate of the reaction, and that's why it's only the alkyl halide, and that's why in previously I gave you factors. Now the factors that I gave you earlier is concentration of each reactant, and now each reactant, now in this one, in SN1 that I'm talking about now, only the alkyl halide is considered. The nucleophile is not considered, only the alkyl halide is considered. So now this is the rate equation. We can put raised to the power 1 if you're used to that, raised to the power of 1. That's it. So that's the rate equation. So now the reaction mechanism is a two-step reaction mechanism. I'll talk about that and I'll explain it later. Now, they include homolytic fission of alkyl halide and attack of carbocation by a nucleophile. Carbocation, also known as carbonium ion, but I love using carbocation because it sounds more like what I've been used to from my young age. That is cation and anion. Carbocation, we all know. That's just what I'm just trying to talk about. You can, from carbocation, just positive carbon ion. That's why it's called a carbocation. So the name shouldn't confuse you. You can just actually break it down later on. Now, I said the first step. That is what I'm going to be indicating now. This is the first step. Yeah. That is the RX, the homolytic fission of the alkyl halide. Now, we all know that this alkyl halide bond, is a polar bond. Yeah, it's polar, but because of this R group, we cannot actually determine that it's polar or it's non-polar. But let's just assume it's polar. Let me just start with the basic one, so I won't end up confusing someone, because we can have the R group indicates infinite number of carbon atoms, and due to the presence of infinite number of carbon atoms, that can actually decrease the polarity, because we all know polarity will decrease. Something like CCCCl, this will be more polar than this and more polar than this, and at the end of the day, due to the long chain carbon atom, because of the R group, we can end up seeing that group will end up becoming non-polar. So let me just use a basic example. Let me use methyl chloride. So I have methyl chloride here, and just put this H3 here. Now this is my methyl chloride. Now what I'm saying is that the homolytic fission, but I was talking about the polarity. Now we all know that electrons, these two bonds, because of like the polarity and every single thing, we end up finding out that this is electron deficient and this is electron what word can I use? This electron deficient, or that this lacks electrons, this has more electrons, is ending up taking more electrons, and that will be something like this if you're actually going to be drawing the shape. This is like the electron concentration. More electrons end up residing here than residing here. We can see that in many bonds. I'm not talking about polarity now, so let me just keep that aspect and just talk about homolytic fission of the alkyl halide. Now, homolytic fission of the alkyl halide, we can see from the equation of the reaction, the alkyl halide ends up splitting. Now, the R group will end up taking a positive charge, and X group will end up taking a negative charge. That is because it's going to end up taking the electron out, and this will end up becoming electron deficient, electron rich. That's a good word. So electron deficient and electron rich. Now, the electron deficient, what did I tell you about nucleophile at the beginning? They are electron pair donors. That means they have excess electron and they can actually just donate those electrons. They are Lewis bases. Lewis bases are electron pair donors. So that means they have extra electron. That means this nucleophile that we see here, it's going to be having extra electron pairs. This is like an imagination of what I'm just trying to say. It's going to be having extra electron pairs. This is electron deficient. This is electron rich. It can actually just donate two of its electrons down to the alkyl group and actually just bond with it and end up forming a bond, and that bond can be any type of bond. If the nucleophile can be any type of nucleophile, and that can lead to any type of bond. I'll indicate this example with OH group. The OH group, that means I'm going to be forming an alcohol later on, but okay, let's just go on and let me just indicate. Now, like I said earlier, what's the first? So let's take an example. Let's take an alkyl halide. Let's take a tertiary alkyl halide. I'll tell you the reason I'm taking a tertiary alkyl halide instead of me to be taking a primary, but let's take a tertiary alkyl halide. So let's use T-butyl. So we have something like this. T-butyl, C, and this ends up becoming Cl. Now we are completing this by putting our CH3, H3, H3, and now this is our T-butyl. This is a tertiary alkyl halide. Now I told you I'll tell you the reason why I choose the tertiary alkyl halide later on, but let me continue my example. What did I say is the first step? The splitting of this. That means this will split into this CH3. Oh, I need to erase this because I need the space. So I need the space to actually keep writing. So this is RCl. Now I said it will split to this CH3. Sorry. So now CH3, this is the first CH3. Now this is the main alpha carbon. This is CH3 again, and this is CH3 plus Cl minus. So this will have a positive charge. Now this is a carbocation, and this is a carbocation. Yeah, this is a carbocation, and this is the chloride ion. Now this is our first example. I told you 10% chloride, and now it ends up following the first step, like I gave you, formation of that is the homolytic fission of the alkyl halide. Now you can see that this alkyl halide actually just fused, and it ended up forming the carbocation, that is the T-butyl carbocation, and the chloride ion. Now the second step, like I told you, is the attack. I told you that the example I'm going to be using is the OH nucleophile, OH minus nucleophile. We can use any other nucleophile. We can use water. We can use any stuff. But I also want to make this example basic because we all know alcohols. So I'm actually going to be forming an alcohol later on. So now let's just go on. Now this T-butyl, like I said earlier, this T-butyl, C, now CH3, now CH3. Let me take this so it won't end up confusing you. Another CH3, another CH3, positive charge. We end up bonding with the nucleophile, I'll explain something later. I'll end up bonding with the nucleophile. That's this OH group, OH minus, and it will lead to the formation of alcohol, CH3. And to reduce this so I can have enough space to write, this is a positive charge, this is the OH group minus, so, and this is C. So let's take this off. This is CH3. CH3, this is another CH3, and this is OH. So this ends up forming tet-butanol. Now we can see, like, these are the two steps of nucleophilic substitution. We all know substitution mechanism, that's displacement of one to another. Now I just like give the mechanism of every stuff happening. Now what I was trying to say, I'm going to explain later on, is because now look at what I'm trying to explain. We all saw this slow and fast here. Slow. Let me remove this. So we also saw this slow and fast earlier on. Now that means what I'm just trying to say is that the first step, that is the homolytic fission of the alkyl halide, is a very slow step. It's a slow step. That means it doesn't occur quickly. It takes time for it to fuse, for it to like break up, the bond to break up, and that first step is a slow step. It's a two-step reaction mechanism, like I said earlier. The first step is a slow step. The second step, that's the like attack of the carbocation by nucleophile, is a fast step and it occurs fast. That's just what I was just trying to explain. So let's go back to our example. Now we can see, like, from what I'm saying now, the first step that involves like CH3. It's actually just breaking down into like the tet-butyl chloride broke down into tet-butyl carbocation and chloride ion. Then it's then attacked. Then tet-butyl carbocation is then attacked by the OH group, that is the nucleophile, and leads to the formation of tet-butanol. Now that's just everything you need to know about SN1 reaction mechanism, substitution nucleophilic unimolecular reaction mechanisms. But right now I'm going to be talking about the factors that favor SN1 reaction mechanism. Now SN1 reaction mechanism don't just occur like that. There are factors that actually favor this reaction mechanism. Now I'm going to be talking about the three factors. Now the first factor is presence of two or more alpha carbons attached to the functional group. Like I said earlier, I gave an example with a tertiary alkyl halide instead of me to use a primary alkyl halide, and I told you I'll give you the reason for that. Now this is the time I gave you the reason for that. Let's go back to our free page and actually just give the reason for that. Now what I'm just trying to say, why does this occur like this? Because tertiary alkyl halide, CH3 and CH3 forms stable carbocations. Just note that factor. Tertiary alkyl halide forms stable carbocations. Like unlike primary alkyl halides, something like CCl, then a CH3. Whenever this fuses and ends up forming like an alkyl halide, whenever this fuses and ends up forming like a carbocation, it is not stable. CH3 plus a methyl carbocation is never stable. It's never stable. At the end of the day, it's never stable. It doesn't like form a stable carbocation. But tertiary carbocations, they are stable, and that's why I use this example, because I can actually give the reason for its stability, because all the groups around it, this CH3 is electron donating, this methyl group again is electron donating, and this methyl group again is electron donating. There are two electron donating bonds which help to stabilize this missing electron here. So at the end of the day, it ends up becoming stable. Secondary carbocations could either follow SN1 or the next one I'm actually going to talking about, substitution nucleophilic bimolecular. But for tertiary, just know tertiary alkyl halide, they always follow SN1 reaction mechanism. So let's go forward to the next factor. Now the next factor is presence of polar protic solvents. I told you I'm going to be talking about this later. Now polar protic solvents that lack proton. Polar protic solvents are solvents, let me just put it, that lacks proton. If you don't understand what I'm trying to say, they don't form hydrogen bonding. We can see that later on. Let me just like, this point is actually like the main point I'm actually going to be talking about. I'm sorry for that. This point is actually the main point I'm actually going to be talking about. Polar protic solvents, they lack proton. That means they don't form hydrogen bonding. Look at hydrogen bonding is formed between F, fluorine, oxygen, and nitrogen. These are the only three elements on the periodic table that form hydrogen bond. That's the three most electronegative elements ever. Those are the only three elements that form hydrogen bonding. Now, for a solvent not to form hydrogen bond, that solvent is a polar protic. I mean, it's polar and it's polar. It's polar. That solvent is a polar protic solvent. That's why I say polar solvents can also be subdivided into polar protic and polar aprotic. But just know polar protic solvent, they lack they form hydrogen bonding. That's just like what we used to like classify them as polar protic solvents. Now examples are water, ethanol, methanol, ammonia. We all know ammonia has this, water has, all of them, they have all this group. Fluorine doesn't actually is really electronegative. That's why I'm not really giving you an example with fluorine, but just note all of this. These are polar protic solvents: water, ethanol, methanol, and ammonia. And this favors SN1 reaction mechanism. I'll tell you later why they don't favor SN2 reaction mechanism. Now, the third factor is concentration of the alkyl halide. Concentration of the alkyl halide, that's just like the third factor. That's higher concentration and all this other stuff. Now note, in SN1 reaction, the nucleophile is open to attack from either side. That is, if the alkyl halide is a chiral molecule, therefore optically active, the end product is going to be a racemic enantiomeric mixture of RNA. What this complex thing is just actually saying is that, let me just demonstrate here. The alkyl halide, let's just use T-butyl again. CH3, and CH3. When it's attacked by the nucleophile, it ends up forming two mixtures. The nucleophile can either attack it from the left or from the right side, That's if it's a chiral molecule. This molecule is not chiral. Chiral molecules are molecules like when the alpha carbon has like four different like alkyl groups or four different groups attached to it. Let me just make the molecule chiral so I don't end up confusing some people. So now I'm forming a chiral molecule. So I'm going to be using R because I don't have time or the space to be drawing complex molecules. Now this is R prime, and this is R prime raised to power 2. Now these three molecules, note they are different molecules. Let's say this R, let's just say that it's an ethyl molecule, ethyl. This now is a propyl molecule. This now is a butyl molecule. And now this molecule is chiral because it has different atoms attached to like the primary carbon. Now what I'm actually just trying to say is that this nucleophile will actually form a racemic mixture. Racemic, that's an equal mixture of this R prime. The nucleophile can end up coming here, R prime prime, and this is R prime. So this first one is not meant to have a prime. Or it could either, let me remove this. It could either form this, or it could end up coming here and forming this. That means it could end up coming here and forming this R, then the nucleophile will bond here, then the R prime prime, and then the R prime. It could end up forming these two, but at the end of the day, it forms equal numbers of these. That means the atoms of the left one is equal to the atoms of the right one. That means it forms a racemic mixture of both of them. That's just what I was trying to say. Now let's talk about the second point. That's substitution nucleophilic bimolecular reaction mechanism, also called SN2 reaction mechanism. Now this follows second order of kinetics. I told you what first order of kinetics is. Now second order of kinetics, let me just put it like that. From name second order, this is not the real rate equation, but this is like a rate equation because the order of reaction is the power with the concentration is raised to. So now the second order, it follows second order of kinetics, and that will be equal to R, the concentration, raised to the power 2. That's the rate law. That's what is given by. Now in SN2 reaction mechanism, the concentration of the alkyl halide and the nucleophile are considered, hence leading to a rate equation of this. I told you in SN1 the concentration of the nucleophile is not considered, but in SN2 the concentration of the nucleophile is considered. I'll tell you the factor later on, but just note that the concentration of the alkyl halide and the nucleophile is considered, and that's a major difference between SN1 and SN2 reaction mechanism. So let's go forward. Now, another variation between this and SN1 reaction mechanism, it is a one-step reaction mechanism as the halide group as the halide group leaves at the same time the attacking nucleophile attacks the alkyl group. It's a one-step, SN1 two-step, SN2 one-step reaction mechanism. That means as the halide group is leaving, the nucleophile is also attacking. So at the end of the day, the attacking nucleophile bonds to the side opposite to the point where the halide group leaves, and that is called, like, let me just leave this part. The attacking group bonds to the opposite side. That means if the alkyl halide, like, let's just say there's a carbon, if the halide group is leaving here, the attacking group, the nucleophile will come and bond here. It won't be found here. So at the end of the day, let's just say this was with the H3. This was our alkyl halide. At the end of the day, when we are forming like the new product, we end up having this Nu, and this is my H and this is my 3. This is what we end up having. It's always bonding to the opposite side. Now I said that the nucleophile is bonding as the alkyl halide is leaving, and at the end of the day, to lead to a transition state, I'll actually demonstrate that transition state. It leads to a transition state where the nucleophile is still attacking and is still trying to form a bond, and the alkyl halide and the halide bond is still trying to break. So it ends up leading to a transition state, which I'll demonstrate later. Now this other part I just skipped. It's just called, like, the process is called inversion of configuration. If the alkyl halide is a chiral molecule, it's just note that it's called inversion of configuration. That is like the switching of the position from left to right. Only in a chiral molecule. If the molecule is not chiral, it's not going to be called inversion of configuration. I've told you what a chiral molecule is, so I don't expect you to have a problem with that. Now, a transition state is formed in which the halide ion is yet to leave and the nucleophile atom is about to enter. That's what I was demonstrating earlier, and I told you I'm going to tell you what that actually means. Now, like I said earlier, tertiary alkyl halide is favored by tertiary alkyl halide favors SN1. Now, primary favors SN2. I'm actually going to demonstrate that later. So let's use a common example, methyl chloride. Now we have methyl chloride with CH3 with the Cl. Now I told you that it's a one-step reaction mechanism. What do I mean by that? As this bond is fused, as it's breaking, another bond is forming. The nucleophile is coming to attack in the opposite position. That's just what I told you. As it's breaking, the nucleophile is attacking, and to lead to the formation of what did I say earlier? The formation of a transition state. So now let me just illustrate all of those things now in just this board. Now what I mean by that is this: C H H H is a one-step reaction mechanism. Fusing. Now what actually happens is that as this bond here, because we all know this bond is meant to break for the nucleophile being OH minus, same example I'm using, is coming to attack. So we all know this bond is meant to break, but the bond is breaking. As the bond is breaking, the OH is also attacking. So it ends up leading to the formation of this transition state. Let me put my H here and my second H here. Then my third, let's put it down. Then the OH is bonding. So let me just erase this entire stuff so I can actually get the space to actually like illustrate what I'm saying correctly. So I have the C. Now the H is here, and the second H is here, and the third is here. Now the OH is coming to attack. This is the OH. It's still attacking. It's still bonding. We can see from the double line that it's still forming a bond, and this bond is still leaving. Cl. So I can just illustrate with an arrow. This is leaving and this is forming. This is forming and that is leaving. And this state that is actually going to form now, this state that I just drew, is called the transition state that I was actually talking about earlier, whereby the OH bond is not completely formed and the Cl bond is not completely broken. That's just what I was trying to say earlier. Now that's all about SN2 reaction mechanism. Now let's just talk about the factors that SN2 reaction mechanism depends on. Now, I've given you the factors which SN1 reaction mechanism depends on, but now SN2 reaction mechanism, like I told you earlier, presence of less or equal to 2 alpha carbons attached to the primary carbon. That is 2 or less, 2 or 1 carbon attached to the alpha carbon. And that's like the first one. That's why I told you primary alkyl halides favor SN2 reaction mechanism. Presence of polar aprotic solvents. Polar aprotic solvents are solvents that do not form hydrogen bond. Polar aprotic solvents are solvents that form hydrogen bond. They are always going to be polar solvents. They are polar. They must be polar. That's just something you need to know. So example of polar aprotic solvents: DMF, that's NN dimethylformamide, DMSO, dimethyl sulfoxide, acetonitrile, and acetone. There are other examples, but these 4 examples are the common examples. That's why I gave you the examples. Now, polar aprotic solvents, like I said earlier, are polar solvents that cannot form hydrogen bond. That's this point. They're polar solvents that can't form hydrogen bond. Now, I told you I was going to give you a reason why. I told you I was going to give you a reason why why polar aprotic solvents favor SN1 instead of SN2. Now, in SN2 reaction mechanism, we all know that the hydrogen... Okay, let's go back and let me just illustrate with this page. Now, the hydrogen bond, HF, let me use HO, OH minus. This will end up being electron rich and this end up becoming electron deficient. That means this is having just use the positive means electron rich and the bad means electron deficient in my example now. Now, this is what I'm just trying to say. This ends up becoming electron rich, this ends up becoming electron deficient. So that means this will have a positive charge attached to it. So let me just act as if I'm breaking it down, the OH group. Let me just act as if I'm breaking it down. So if I'm breaking it down, have something like O minus. It's meant to be O2 minus, we all know. So let's put the 2 here, O2 minus, or let me just remove that so I won't end up confusing people. So it's meant, let me just use O minus plus H, positive charge. Now we all know that the nucleophile, what do we know about the nucleophile? Nucleophile is electron rich. So at the end of the day, this nucleophile, instead of it to end up attacking the alkyl group, because this is also electron deficient, that means the polar aprotic like solvent is also electron deficient, it can end up attacking both the alkyl group and end up attacking this group again, this hydrogen. And at the end of the day, it ends up forming a complex product, a product that we don't expect. We want a substitution reaction to occur, and at the end of the day, we are getting a different product. We might end up forming water, might end up forming any other product that we don't actually need, and that's why it's mostly favored by SN2 reaction. That's why I said that polar aprotic solvents, like, it doesn't favor SN2 but favors SN1. Okay, that's all about that. So let's just go further and keep talking. Now, the third factor is concentration of the alkyl halide and the nucleophile. Like I said earlier, the concentration of the alkyl halide and nucleophile are considered here. So the fourth factor is steric effect of steric hindrance. Now look at tertiary, like the example I gave you before. I gave you T-butyl for SN1 reaction mechanism. T-butyl has, T-butyl has C, C, C. All these C's, they have their H, they have their H, they have their H. This has another C, he has his H, he has his H, it has his H. This has C again, it has his H, 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 H. And at the end of the day, we are seeing a bulky group. This is like the full structure of what we're talking about. Now, even nucleophile, because I told you that the nucleophile ends up like bonding in the opposite direction as the alkyl halide. That's what I told you. As the chloride, as the halide group that is leaving. So the Cl is leaving here. The nucleophile is expected to come and bond here at this position. If I may use a different color, the nucleophile ends up, it's coming to bond here at this position because the halide is leaving at this position. But now this nucleophile has to face a challenge to bond. It has to overcome this. It has to push this to another side. This group is bulky, and that's steric hindrance. For it to end up bonding there, it has to, like, what should I say, push its way into that place and form a bond here. And that's what I'm just trying to talk about. It has to push its way there and form a bond here, a new bond here. And that's not possible because of the bulky group. This methyl group is not even bulky enough to illustrate my example. What about if we have other forms of bulky groups? What we have said, it could have been tough for it. So that's steric hindrance. And alkyl halides which has the head carbon bonded to only one atom will more likely undergo SN2 reaction mechanism compared to one with 5 bulky atoms attached to its head carbon. That's another reason why primary alkyl halide undergo SN2 instead of SN1, because of steric hindrance. In primary alkyl halide, there's little or no steric hindrance, but in tertiary there's steric hindrance and steric effect, and that will actually reduce the bonding capability. So now, from what I've explained, like everything I've talked about now, we've seen that primary alkyl halide are mostly favored by, primary alkyl halide favors SN1 reaction mechanism, tertiary favors SN2 reaction mechanism, secondary could either undergo SN1 or SN2 reaction mechanism. Secondary could either undergo the first or the second one, depending on what factor you subject it to. You can change, I told you the factors, you can change the polarity of solvent use, you can change whatever factor, the concentration, whatever, and that will determine the rate step you want it to actually undergo. But it can undergo either SN1 or SN2. So I think that is all. I think that's all I was meant to talk about. Yes, so thank you for watching. Please like and subscribe for more of these videos explaining organic chemistry. Okay, goodbye.